Okay guys, another video here. We're going to continue our discussion of precipitation. This is an application of precipitation reactions called selective or fractional precipitation. And the idea here is that you have perhaps some ions together in solution. In this case, we're talking about barium ions and strontium ions present in the same solution. And the goal is to separate those ions from one another. And so we do this by selectively precipitating one ion over the other one. And so what we'll note here is that both barium and strontium can be precipitated with chromate ions. And here are the KSP expressions for barium chromate and strontium chromate. And they have different KSP values. And the thing to note is that the KSP for barium chromate is much, much smaller than the KSP value for strontium chromate. That means that barium chromate is much less soluble than the strontium chromate. And if you add the chromate in very slowly, you can build up the level of chromate gradually, and you'll get to a point where the barium chromate will start to precipitate out. But the strontium chromate, the concentration of the chromate isn't high enough to get the strontium chromate to precipitate out. And so this is how selective precipitation works. Let's go through the details. What you can do is calculate at what chromate concentration is required in order to get the barium chromate to precipitate. Likewise, you can do a calculation for the strontium chromate. And so those calculations are laid out here. I'm taking the KSP expression and I'm rearranging it and solving it for the chromate concentration. When you do that, you find that the barium chromate will precipitate out at 1.2 times 10 to the minus 9 moles per liter chromate concentration, whereas the concentration of chromate required to precipitate out the strontium is much higher. So if you add the chromate in very slowly, you'll get the barium chromate to precipitate out of solution before the strontium chromate has had a chance to precipitate. In this follow-up question, we're asking, well, let's suppose that we precipitated out the barium, and then we've just reached the point where the strontium has started to precipitate out. So the chromate concentration has reached 3.5 times 10 to the minus 4 moles per liter. The strontium is about to start falling out of solution. How much barium is still left in the solution? And so the idea here is to take the KSP relationship for the barium chromate and substitute in this chromate concentration, the 3.5 times 10 to the minus 4, and solve that for the barium ion concentration. So we do that here. We rearrange this KSP and solve it for barium, but substitute in this concentration for the chromate. And at that concentration, we find that the barium concentration has been reduced to 3.4 times 10 to the minus 7 moles per liter, which is a lot less than what we started with. So indeed, you can effectively separate the two ions using this selective precipitation approach. Here in this conceptual example, we are trying to separate iodide ions from chloride ions. So we have a solution where we've got some potassium iodide and we've got some potassium chloride. You can use silver ions to precipitate out the silver iodide and the silver chloride. And so if you add silver nitrate gradually and let the silver concentration build up slowly, you can selectively precipitate these two ions. And the question is, which of the precipitates will form first? And to figure that out, what we need to do is compare the two KSP values. And so we see for the silver iodide, the KSP value is much smaller than the KSP for silver chloride. That means that the silver iodide is much less soluble, hence it will precipitate out at a lower silver concentration than the silver chloride. This is a similar example, but there's a follow-up numerical problem for it. And so again, we're looking at the precipitation of halides using silver. This time it's silver bromide and silver chloride. We've got the same question: which of these two are going to precipitate first if you gradually add the silver ions? And we see that the silver bromide KSP value is smaller than the silver chloride KSP value, so we would expect the silver bromide to precipitate out faster. At what concentration of silver will the silver bromide begin to precipitate? We take the KSP expression and we rearrange it and solve it for the silver ion concentration, substituting the values from the problem, and we get a concentration of 1 × 10⁻11 moles per liter. In this next topic, we are considering how the solubility of a particular compound is affected by the presence of a common ion. And by that I mean we've got this solution at equilibrium, and let's suppose that we add in lead nitrate, for example. So we've got lead ions and chromate ions in solution. What will happen if we add lead nitrate in? Well, from Le Chatelier's principle, we know what will happen. If you increase the concentration of this product, it's going to drive the reaction a little bit to the left. That's going to result in the formation of a precipitate, and we would say that the solubility of the lead-2 chromate is smaller in the presence of a common ion. So here is an example problem illustrating the common ion effect. In this problem, we are considering the solubility of cadmium sulfide, and so here is the dissolution reaction for that, but we're considering the solubility in the presence of a common ion. So we have in the solution 0.01 molar cadmium bromide, okay, and so the ion in common in this case is the cadmium. And to work this type of problem, we need to set up an ice table to help us. And so here I've written the initial concentrations. You'll note that for the cadmium, the initial concentration is not 0. It's 0.01 molar coming from the cadmium bromide. But the concentration of the sulfide is initially 0. And so what's going to happen is some of the cadmium sulfide is going to dissociate. That's going to give us a little bit more cadmium ions and some sulfide ions. And then to get the equilibrium line, what we need to do is add these two together. And it looks like I have a typo. I've gotten these switched around. So this 0.10 plus S is supposed to be right here, and then the S by itself is supposed to be right there. So I've got these two switched around. So keep that in mind. Anyway, once you get the equilibrium concentration line worked out, you substitute those expressions into the KSP expression. And so for the cadmium, it looks like I've corrected it here. For the cadmium, you have 0.01 plus S, and for the sulfide, you have S. This would result in a quadratic equation that you would have to solve for the solubility. However, in these types of problems, the value of S relative to a number like 0.01 is going to be completely insignificant. How can we understand that? Well, this compound is not very soluble to begin with. So even without the common ion present, the value of S is very, very small. But when you add a common ion, it's going to push the equilibrium to the left, and so the solubility is going to get even smaller. So you can definitely make this approximation where we neglect the plus S relative to 0.01. And that's what I've done here in this last expression. Then it's very easy to solve for the solubility. In this case, you just take KSP divided by 0.01, and it gives you a solubility of 1 × 10⁻26 moles per liter. So very, very small. For comparison's sake, what would be the solubility of cadmium sulfide without the common ion? And so this would be a separate problem, much like we did in the first video. Let's just consider cadmium sulfide by itself, no cadmium bromide present, and calculate the solubility of that compound from the KSP value. You find that you get a solubility of 1 × 10⁻14. But then when you add the common ion in, you see that the solubility drops by several orders of magnitude. So indeed, the common ion effect pushes the equilibrium to the left, the cadmium sulfide certainly becomes less soluble in the presence of a common ion. Here's another example where the stoichiometry is a bit more complicated. It's not too bad though. We're considering the solubility of aluminum hydroxide, and we want to know what is the solubility of aluminum hydroxide in the presence of a common ion. That is, if we add aluminum nitrate to the solution, how will the solubility of the aluminum hydroxide change? So here's the dissolution reaction of interest. We set up our ice table. The initial concentration of the aluminum ion coming from the aluminum nitrate is 0.015, so I put that in the initial concentration. Initially, we don't have any hydroxide yet. A small amount, minus S, of the aluminum hydroxide is going to dissociate. That's going to give us a little bit extra aluminum ions, and it's going to produce some hydroxide ions. To get the equilibrium line of the ice table, we add these two lines together. So we've got the 0.015 plus S. Again, that plus S is going to be completely insignificant, so we can just neglect it. And then we'll have 3S for the hydroxide. We substitute these concentrations into the solubility product. And then, if it weren't for our approximation, we would have a fourth degree type of polynomial to solve. However, we know that S is going to be very small, so we'll just neglect this. And then we get an equation that's much easier to solve for the solubility. We just take the KSP, divide it by these constants in front, and then take the cube root. And it gives us 3.7 times 10 to the minus 11. What would be the solubility without the presence of the common ion? I think we worked this exact problem in the first video in the solubility series. S would be equal to the fourth root of KSP divided by 27, and you get a value of 5.2 times 10 to the minus 9. So when you add the aluminum nitrate, the common ion, you see that the solubility drops 2 orders of magnitude at least. So I'm going to stop this video right here.